Hi everyone, I'm Sneha S. from Sri Venkateshwara College of Engineering, studying in third sem. Today I'll be dealing with the topic called observing state of a Markov chain. So let us begin. Definition. A type of Markov chain in which when a certain state is reached, it is impossible to leave that state. Such states are called observing states. And a Markov chain that has at least one such state is called an observing Markov state. Let us look at this example. So here S2 is the observing state. It is a state which cannot be left. So that's why we are calling it as an observing Markov state. And whenever you add the rows, the sum will always be equal to 1. Introduction. The observing state in a Markov chain refers to a state from which it is impossible to transit. In other words, once the chain enters an observing state, it remains in that state indefinitely. Observing states have a probability of 1 for remaining in that state in the next step. To identify the observing state of a Markov chain, you can look at the transition probability matrix. Observing state can be identified by having a diagonal element 1, indicating that the probability of transitioning from the state is 1 itself. Other elements in the row corresponding to the observing state will be 0, indicating that there are no transitions from the observing state to any other state. Here is an example for transition probability state. Properties of observing state of a Markov chain. Observing states can exist in both finite and infinite Markov chains. In a finite Markov chain, there must be at least one observing state. Observing states can be transient or recurrent, depending on whether it is impossible or possible to return to them from other states. Observing states from closed subchains within a Markov chain. Once the system enters an observing state, it will remain in that state forever. Observing states can also act as observing barriers, preventing the system from reaching certain states. These are some properties of Markov chain. How do we calculate an observing state? To calculate an observing state, the absorption probability of a state is the probability that the system will end up in an observing state. Absorption probabilities can be calculated using matrix algebra, that is, or by solving a system of linear equations. So to find the absorption probability, it should always be equal to 1. So now when here is a question which is here we can calculate the probability of the spinner on red sector, blue sector and green sector. So we end up getting different probabilities, but once you add all the probabilities, the sum will always be equal to 1. This is how you calculate the absorption state. Limitations. Assumes memoryless property. Assumes stationarity, limited to finite state space, assumes homogeneity. So first assumes memoryless property, which means Markov chains with absorbing state systems assume the memoryless property, which means that the future state of the system depends only on the current state and not on any previous states. While this assumption is useful in many applications, it may not hold good in all the cases. Assume stationarity. A Markov chain with absorbing state rely on the assumption of stationarity, which means that the probabilities of being in each state remain constant over time regardless of the initial state. This assumption may not hold good in situations. The stationary distribution may not accurately reflect the long-term behavior of the system. Limited to finite state space. Markov chain with absorbing state are typically limited to the finite state space, while some techniques exist for depending Markov chains to finite state space. Assumes homogeneity. Markov chains with absorbing states typically assist homogeneity, which means all the transition probabilities between the state are constant over time. If the system is initialized in a state with low probability of reaching an absorbing state, the time to absorption may be prohibitively long. Absorption state models assume that the system remains in absorbing state indefinitely once reached. In reality, some absorbing states may be temporary or reversible. Extension to the absorbing state model can be made to incorporate time-dependent or transient absorption. These are some limitations of observing state of Markov chain. Now let us see the applications. Application first one is drunkard's walk. This is a very famous example. A drunkard is one of n intersections between their house and the pub. The drunkard wants to go home, but if they reach the pub, they will stay there forever. So this is an example of absorption state. Next is tennis. To win a game of tennis, you have to score at least 4 points. But you must also have at least 2 more points than your opponent. Diary calls. The absorbing state is the event of having calving occurs. Student progression. Observing Markov chain models can be used to determine factors including expected time within various levels of study, duration of candidature, professor workloads, and academic attainment. Next, chronic disease. Clinical Markov models use death as an observing state. Means once they have reached, if once a person is dead, he will stay in that state forever. Observing states are widely used in various fields including finance, biology, and physics. In finance, observing states can represent bankruptcy or financial success. In biology, observing states can represent extinction or stable population sizes. Means once something is extincted, it can never come back. So in conclusion, Markov chains with observing states are a powerful modeling approach that has a wide range of applications across various fields. While these models have some limitations, they remain a valuable tool for understanding the dynamics of complex systems and predicting their long-term behavior. By representing different states and observing states, Markov chains with observing states can help in assessing risk, optimizing maintenance strategies, evaluating system performance, and more. Thank you. Please like and subscribe to my channel.